Hey guys, Mr. Backerberg here. In this video we're going to be looking at exponential functions and their graphs. So as we're looking at an exponential function, we're going to be looking at something like f of x equals a times b raised to the xth power. Okay, so a and b are going to be real number constants. The a value of our function is called the initial value, and the b value is the base of the exponential function. And a couple things that we need to make sure about those a and b values. We do need to make sure that a value is a non-zero number. We need to make sure that our base for our exponential function, so that b value, that needs to be a positive value, and we also need to make sure that our base is not 1. So we're going to take a look at some functions and try to decide if they are exponential functions or not. If they are exponential functions, we want to identify the initial value and the base of our exponential function. So the first one we're looking at is f of x equals 3 to the xth power. And this one is an exponential function because we have a numerical constant base value and a variable as our exponent. So as we're looking at the initial value of this one, we would be looking for our a value. Now there's not anything being multiplied by our 3, so our initial value is just going to be 1. And the base is the number that the exponent is on, so that's our 3. As we take a look at our next function, we've got g of x equals 6x to the negative 4th power. This one is not an exponential function because the base value is a variable and the exponent is a constant, so this one is actually a power function. As we're taking a look at this function, h of x equals 7 times 2 to the negative x power, we can see that we have a numerical base being raised to a variable power, so yes, this one is an exponential function. This one has an initial value of 7, since we have the 7 times 2 to the negative x power. But as far as the base value goes, this one's a little bit tricky to think about. As we're looking at that 2 to the negative x power, we're actually going to look at rewriting that a little bit. So we can think about this as 7 times 2 to the negative first power being raised to the x. And if we have 2 to the negative first power, when we've got that negative exponent in there, we can actually rewrite that as 1/2 so that we have a positive exponent on there instead of that negative exponent. And then this is still being raised to the x power. So the base of our exponential function is actually 1/2. So in our next example, we're going to look at computing some exponential function values using the function f of x equals 2 to the x. And the first thing I want to look at is f of 4. So that would mean plugging 4 in for this x. So we would have 2 to the 4th power, which ends up being 16. Or if I wanted to look at f of 0, I would need to plug 0 in for my exponent. So 2 to the 0 power, well, if we take a number and raise it to the 0 power, the answer we're going to get is going to be 1. Or if I wanted to look at f of negative 3, that would mean taking 2 to the negative 3rd power. But when we're dealing with negative exponents, we want to rewrite them as positive exponents by turning this into 1 over 2 cubed. And I know that 2 cubed is 8, so we can really rewrite this as 1/8. Or if we wanted to look at f of 1/2, then as we plug in that 1/2 exponent, we'd have 2 to the 1/2 power. But a 1/2 power is the same thing as a square root, so we'd really be looking at the square root of 2. And if we got a decimal approximation there, that's about 1.41. In this example, we're going to look at finding an exponential function from its table of values. So we have a table that has x values in it and then our function values in it. And we're going to try to write out the exponential function that would give us these values. So we know that we're dealing with an exponential function. So it's g of x equals some initial value a times some base value b raised to the xth power. Now we know that when we plug in 0 for our x value, we end up getting a function value of 4. And I'm going to use that to help me figure out what my initial value would be. Because if I take any base value and raise it to the 0 power, the answer I'm always going to get is going to be 1. So we're taking this 1 value times our initial value and getting 4 as the answer. So that tells me that my a value must be 4. Now if I know that my a value is 4, I'm actually going to be able to figure out what this base value is. And I'm going to look at this 112 set of information right here. So we now know that we have g of x equals 4 times some base value raised to the xth power. And when we plug in 1 for our x value, the answer we get is 12. When you raise something to the first power, the answer you get back is just going to be whatever the base value is. So we're taking our base value times 4 and getting 12 as our answer. So our base value must be 3. Now that we have our a and our b values, we should be able to write out our function. So we're going to have g of x equals 4 times 3 to the x power. And we can double check that with the rest of these x values that were given, and we will get back the same exact function values that are given to us in the table. Now going back to our exponential function f of x equals a times b to the x. As we're taking a look at this function, if our a value is positive, and if our b value is greater than 1, as we increase our x values, then our function will continually increase as well. So we can call this an exponential growth model, with that b value being called the growth factor. But we could also have an exponential decay model, and what's going to happen there is we're still going to have a positive a value, but this time our b value is going to be between 0 and 1, so either some fractional or decimal value. So this is an exponential decay function, and our b value is our decay factor. The last thing I want to look at is transforming exponential functions and what those transformations do to the picture of our graph. So we're looking at the function f of x equals 2 to the x, and along the left hand side I've made some different changes to that function. So for my function g of x, I made it 2 to the power of x minus 1. So we can really think about this as f of x minus 1. And what that minus 1 does inside of that parentheses with our x there is a horizontal shift. And remember, horizontal shifts are always backwards of the way that you would think they would be normally. So this minus 1 actually moves you to the right one space. Now as we take a look at our next one, h of x equals 2 to the negative x, we can think about that as f of negative x. And because we're putting that negative directly on the x, then that's going to be a y-axis reflection. And for our last one, for k of x, we've got 3 times 2 to the x. So we can think about this as 3 times our f of x function, which makes this a vertical stretch by a factor of 3. And I'm going to graph these out on my calculator just to confirm their behaviors. So in my calculator, I've got all 4 functions typed in. I'm only going to graph 2 at a time. So we've got our normal 2 to the x, and we've got our 2 to the x minus 1. So if I graph that out, I can see that my red graph got shifted right by 1 space. Now I'm going to go back to my y equals, and I'm going to turn off the 2 to the x minus 1, and I'll turn on the 2 to the negative x, and I'll graph that out. And we said this one was going to be a y-axis reflection, so mirroring that 2 to the x blue graph over the y-axis. Then I'll go back to my y equals, I'll turn that one off, and I'll turn my last one on, that 3 times 2 to the x. And when I hit graph, we said this was going to be a vertical stretch by a factor of 3, so we can see that our pink graph is getting taller faster. That's going to be it for this video. Thanks for watching.